In this video, we're going to look at CC15, which is on energy changes, and this is a paper 2 only topic. Below, I've just written out a kind of a general chemical reaction. I've got A and B reacting with each other to produce C and D. A and B are my reactants, and C and D are my products. Chemicals store energy inside their chemical bonds. So you can kind of think of chemicals as little mini batteries. So underneath here, for the reactants, I'm just going to draw a battery. And we're going to say that between reactant A and reactant B combined, my reactants have this much energy. So that's how full their battery is. When your reactants form products, you are forming something entirely new. So C and D are entirely different than what I started with and what A and B. And again, C and D can store chemical energy. So C and D are also like little batteries. But C and D will not store exactly the same amount of energy as A and B did. Let's say, for example, C and D are going to store less energy than the reactants A and B. Energy cannot be created or destroyed. So if this energy is not being destroyed during this chemical reaction, where is this energy going? As I said, in the chemicals themselves, it's stored as chemical energy, but this energy can be released as heat energy. So as I go from my reactants to my products, heat energy is released. And the reason heat energy is released is because my reactants A and B are capable of storing more energy than the products I'm making, C and D. Because they store more energy than my products, some energy must be released when I'm forming my products, and that energy is released in the form of heat. If heat energy is being released when a reaction is taking place, then the temperature of the surroundings, which is where you're doing your chemical reaction, the immediate surroundings, the temperature of the surroundings is going to increase. The surroundings will get hotter. So an explosion will be an example of an exothermic reaction. That's an extreme example. It releases a lot of heat and the surroundings are going to get a lot hotter. You can also have another situation, which I've got drawn below. I've got my reactants, A and B, forming products, C and D. But this time I'm going to say that my reactants, A and B, they don't store a lot of chemical energy, whereas my products, C and D, store quite a bit of chemical energy. So if I want to convert A and B into C and C and D have more energy than A and B, then I'm going to need to put energy into this reaction in order to make my products. Again, that energy is going to be in the form of heat. So you're going to be adding heat to the reaction in order to form your products. That heat energy is going to be taken from the surroundings, and because the reaction is going to absorb heat energy from the surroundings, the temperature of the surroundings is going to decrease. Okay, so to go from A and B to C and D, I'm going to need to absorb heat energy because C and D have more energy than the reactants. And in order to form my products, you're going to need to absorb energy because the reactants themselves don't contain the required amount of energy. The reaction that I've got on the top, the reaction that released energy to the surroundings, this is called an exothermic reaction. So you can remember it as thermic is heat and exo is kind of like exit. So the heat is exiting the reaction because the products have less energy than the reactants. Temperature of the surroundings will increase. And the opposite of exothermic is endothermic. The heat is entering the reaction, it's being absorbed from the surroundings, and the temperature of the surroundings is going to cool down. I've made a little table here that summarizes these two reactions. So exothermic releases heat energy to the surroundings, causes an increase in temperature, and endothermic absorbs heat energy from the surroundings, it causes a decrease in temperature of the surroundings. As well as knowing what exo and endothermic reactions are, you need to be able to draw what we call a reaction profile diagram. On my reaction profile diagram, you're never going to have numbers, you're just going to have heat energy on the y-axis, but you won't be given any numbers. And what you're going to do is just show how the heat energy changes as you go from the reactants to the products. With our exothermic reaction, we saw that the reactants started off with lots of energy, but because that energy was released, the products have less energy than the reactants started with. So to show this, because the reactants have more energy, I'm going to draw a line for the reactants and I'm going to put it quite high on the y-axis to show that my reactants are starting out with lots of energy. For the products, because energy is being released, my products are going to have less energy than my reactants. So I'm going to draw my products lower down on the y-axis to show that my products have less heat energy overall. Again, you're not going to be given numbers to plot here. You just need to put the reactants up high on the y-axis, the products down lower to show that the reactants have more energy than the products. The reason the reactants have more energy is because during your exothermic reaction, heat energy is released. Okay? If I do the same for my endothermic reaction, remember with the endothermic reaction, the products have more heat energy than the reactants did. So I need to show that the reactants are starting out quite low. They don't have a lot of heat energy, but that my products are up higher on the y-axis. They have got more heat energy than my reactants have. So exothermic, reactants up high, products down low. Endothermic, reactants down low, products up high. The other thing I need to do on this reaction profile diagram is show the activation energy. So the activation energy is the minimum amount of energy required for a reaction to take place. It's kind of like a pass mark in the exam, the minimum amount of marks you need in order to pass. With a reaction, it's the minimum amount of energy that the reactants need to have in order to be able to react. Both reactions are going to have an activation energy, and to show this, all I need to do is draw a little hill. So I'm going to join my two lines, my reactants, my products, but I've got a hill. And this shows me that even if I've got my reactants, I need to initially put some energy in so that they react, but then once they react, the products that they're making are lower in energy. I'm going to label this the activation energy. And notice that I start my arrow at the reactants and I end my arrow at the top of this hill. That's always where you start your arrow, at the reactants, and end at the top of the hill. I'm going to do the same thing for my endothermic reaction. Because it's an endothermic reaction, you need to put energy in. That activation energy is going to be a lot larger. Remember, I always start my arrow from the reactants and take it to the top of the hill. So you can see that my arrow for my activation energy in an endothermic reaction is a lot higher. That tells me I need to put a lot more energy in order to get the reaction started. And the reason for that is because your products are higher in energy than your reactants. So you're going to need to put quite a lot of energy in to get this reaction going. If you're asked to draw these diagrams, you're going to get 3 marks for it. You get 1 mark for having the reactants on the left-hand side. So it should always be reactants on the left, products on the right. You get a mark for showing the reactants and products at the right heights. And then if you're asked for it, you will get an extra mark for labeling the activation energy. Just note that the arrow should start at the bottom of the reactants to the top of the hill. So the endothermic reaction diagram, that activation energy arrow is a lot longer. Often what students do is they just start the arrow there, but it's from the reactants to the top of the hill. Okay, so that's exothermic and endothermic reactions. The only other thing you can really be asked is an example. So I've said explosions should be combustion reactions. You can also say neutralization reactions. So combustion is just burning something in oxygen. Neutralization reactions between an acid and a base. You can also have displacement reactions, which we looked at in CC15 when you've got halogen displacement reactions. You also look at displacement reactions when you look at metals. So those 3 types of reactions are always exothermic. Endothermic, some precipitation reactions are endothermic. but it can vary. Okay, so precipitation can be exo or endo, whereas these ones are always going to be exo. We'll just have a look at some exam questions on this so you get an idea of what you're going to be asked. So I've got one here which will be relatively straightforward. It tells you that a chemical reaction is taking place and the temperature changes from 20 to 16. Okay, so you're starting at 20, you're ending at 16. There's been a decrease in temperature. What type of heat change occurs? Because you've got a decrease in temperature, it's going to be an endothermic reaction. So we said that the temperature of the surroundings will decrease. In this case, the surroundings is just going to be the solution that you're carrying that reaction out in, and it decreases by 4 degrees. It means it's an endothermic reaction. If we look at some other ones here, this would what an activation profile diagram question would look like. They tell you that this reaction is exothermic, and they ask you to draw and label the reaction profile diagram identifying the activation energy. It's for 3 marks because it's exothermic. You'll start with the reactants up high, you'll have the products down low, and then you'll draw your activation energy in. So it'll be exactly the same as what I've just drawn, and that's going to get you 3 marks. And you are told that it's exothermic, you just need to draw it. You'll see that they've labelled the axes for you as well. Another question on this. They talk about a reaction here, and it says during the process the temperature of the liquid decreases. Describe how you could measure the change in temperature. You could use a thermometer to get the temperature at the start, use a thermometer to get the temperature at the end, and it asks underneath what type of chemical change causes a decrease in temperature. If it's a decrease in temperature, it's going to be an endothermic reaction, so you would tick B. Another question here, they tell you the temperature at the start is 23, the temperature at the end is 24.7. They want you to explain how these results show the reaction is exothermic. You would say there is an increase in temperature, therefore heat energy is being released. So the reaction is exothermic. So just mention the increase in temperature and say that heat is therefore being released. Another one of these questions, again, they're asking you for they're asking you for an exothermic reaction. You draw it exactly the same as we did before. However, it doesn't ask you for the activation energy, which is why it's 2 marks and not 3 marks. So when you are not asked for the activation energy, you don't need to draw that hill. You'll just draw your reactants on one side, the products down low, and just one straight line joining the 2 of them up. You don't need to draw in the activation energy hill. The rest of the exam questions here. Oh, this one actually. The neutralization is an exothermic change. What happens to the temperature? If it's exothermic, you'd expect the temperature to increase, okay? It's releasing heat energy that surroundings are going to increase. So temperature increases in an exothermic reaction. Oh, this one here, an instant cold pack. They want to know, why does the cold pack become cold when the water mixes with the crystals? So inside a cold pack, you've got a chemical reaction taking place. When that chemical reaction takes place, the cold pack feels cold. It feels cold because the reaction is absorbing heat energy from the surroundings. So the reason that the cold pack becomes cold is because an endothermic reaction is taking place. That endothermic reaction is absorbing heat from the surroundings, causing the surroundings, in this case the cold pack itself, to feel colder. So for your mark here, you would just need to say an endothermic reaction is occurring, which absorbs heat. The rest of these exam questions I will be going through in the next 2 videos on energy changes.